Welcome back. We're here in our Chapter 8 material on thermodynamics, thinking about the energetics of our chemicals and their reactions. In this second video, we'll be looking at entropy and trying to decide what makes a reaction spontaneous and how can we determine if a reaction will be spontaneous. We can start with some terminology. Spontaneous processes are ones that occur without any outside intervention. These are processes that will just happen. We don't need to force them to happen. They'll just happen by themselves. Non-spontaneous processes are ones that don't happen naturally, that don't happen without outside intervention. They might actually happen, but they need to be forced to happen. Notably here, we're not thinking about kinetics in this chapter. Spontaneous can be fast. Spontaneous can also be very slow. It doesn't matter, right? If we're thinking about a combustion reaction, this does happen very quickly. We could also have maybe a radioactive decay reaction, which is also spontaneous, but only happens a few times every 1,000 years. It doesn't matter. Both can be spontaneous, and we'd like to understand why both get to be spontaneous and determine when they are spontaneous. Tying this back to what we talked about in our previous video, many of our spontaneous processes are going to be exothermic, things that release heat. Combustion, it does happen spontaneously once you get it started, and it does release a lot of energy. Great. Other things can still be spontaneous, but also be endothermic. For example, melting happens spontaneously for ice when we're at room temperature, but that's going to be an endothermic process. It will absorb heat in order to melt. Well, why is that melting process spontaneous? Why are these burning processes spontaneous? What drives this? How can we figure out which ones will be spontaneous and which ones won't? To answer that question, we need to introduce a new concept. Entropy is going to be our driving force for spontaneity. For spontaneous processes, the entropy of the universe has to increase. Or put another way, the universe will tend towards more entropy. You might see entropy and disorder used somewhat interchangeably. Entropy is going to be defined based on the number of microstates available for our substance. How many ways can we shuffle around our atoms and molecules in our material? How many ways can we shuffle around the energy in our material? The more ways that we can shuffle things around, the more disorder, the more entropy. We can look at an example here. If you have something like sodium chloride, this is a solid, but when surrounded by water, it will spontaneously dissolve. This can happen because the entropy of the universe is increasing. When we have sodium chloride as a crystal, there are limited ways for us to rearrange our atoms inside this crystal. There's a pretty rigid structure. When it dissolves, there's going to be many, many, many more ways of arranging our substance. Many more microstates available, much more disorder. Therefore, this dissolving process vastly increases the entropy of our universe. Entropy is a thermodynamic function, describes the number of ways that we can arrange our atoms and our energy within our system. Each individual way of arranging our atoms and our energy can be called a microstate. The number of microstates, we can give this the symbol W. And so our entropy, S, is going to be a constant times the natural log of the number of microstates. K here, it is a constant. It's known as the Boltzmann constant. It's Avogadro's number and the gas constant smushed together. 1.38 times 10 to the negative 23rd joules per Kelvin. What this means if we have a certain substance, maybe it's a very simple one with maybe one blue atom and two white atoms, we can try to think about how many ways we can arrange our atoms to build this structure. Well, if we have 3 atoms in a triangle, we can have this one that I've drawn here, or alternatively, we can put that blue atom in a different location, or maybe a third possible microstate, we can move that blue atom up to the final position. With these 3 atoms, 2 white ones and a blue one, there seem to be exactly 3 microstates based on the positions of our atoms. In this very simple example, we have W is equal to exactly 3. From here, we can calculate the exact amount of entropy for our system. Now, this is an incredibly simple example. In real life, we're never going to have really just 3 atoms sitting around. We're going to have thousands upon thousands upon thousands of atoms. Our real life sized structures have billions upon billions of atoms. The number of microstates is going to very quickly become too many for us to even try to count. In addition, we need to consider not just the positions of our atoms, but also the energy stored within those atoms. How many microstates do we have based on the energetics instead of just the positions? Once again, we need to really simplify our picture to calculate some exact amount of entropy. However, this simplification and this formula does allow us to get some very interesting conclusions. In the simplest of all possible cases, if we have a pure substance with all identical atoms and exactly 0 energy, if it's at a temperature of absolute 0, well, there's only one way to build our structure if everything is exactly the same and in a nice perfect crystal, and with no energy to shuffle around, there has to be only one possible microstate. In this theoretical example, we have one microstate and the entropy is exactly 0. We call this the third law of thermodynamics. The entropy of a perfect crystal is exactly 0 when it's at 0 Kelvin. Well, every real life situation is going to be different than that, is going to have maybe some imperfections and definitely some energy to shuffle around. And so every real life situation will have some amount of entropy more than 0. We have a practice problem here. Really, it's the example I drew before, but with perhaps better pictures. How many microstates are available for our crystal? Well, with one unique atom in this triangle of 3 atoms, there's 3 places to put it. We're going to have exactly 3 microstates. Based on this, we can calculate our entropy. 1.5 times 10 to the negative 23rd joules per Kelvin. We have our entropy equation if we can count up the number of microstates. Well, we can also just do some comparisons if we have some intuition about our structure. We don't need to count the number of microstates in order to decide which one has more microstates. So, question A, ice compared to water. Solid ice, these molecules are packed together. We have a rigid, defined structure. When we have liquid water, these molecules are able to move around, vibrate around, rotate around, and therefore have many more possible microstates. Going from the solid phase to the liquid phase, liquid is going to have much more entropy. No calculation required. Likewise, if we have solid salt or dissolved salt, well, in that ionic solid, there's only a few possible microstates. It's packed together and rigid and a very defined structure. Low entropy. Once our salt is dissolved, those ions are free to move around and float around, many more positions for them to be in. Our dissolved salt has to have more entropy. Again, no calculation required. If we're looking for some trends and some intuition, well, we can say that our entropy has to increase as our temperature increases. Right? More thermal energy means that there's more ways to shuffle that energy around, more ways to distribute that energy. Even better, as our phases become less condensed, the entropy has to increase as well. Solids have much less entropy than liquids, which in turn have less entropy than gases. For the same reason, solids have much less entropy than solutions, right? Just like we saw on the previous slide. This can be our first step. Let's look at the phases first when we're trying to decide the relative entropy. If we have things that are the same phase, then we can move on to these different tiebreakers. Maybe temperature, maybe molecular size. The bigger our substance, the more ways for it to flop around and twist around and arrange itself. Larger molecules will have more entropy. We can also have substances with different degrees of freedom. Something like graphite is not nearly as rigid as something as diamond. More rigidity leads to less entropy. Or likewise, the molecular complexity, how big and complex our molecule is, will lead to more molar entropy. As we said, though, those can be kind of tiebreakers. Our first place to look is probably going to be our phases. Couple of practice problems here. Which do we expect to have more entropy? Potassium iodide, potassium bromide. Well, these are both solids, so we'll need to move on to one of our tiebreakers. Iodine compared to bromine. Well, iodine is going to be a larger atom. Bigger atoms, bigger molecules will have more entropy. For B, silver chloride as a solid compared to silver chloride that is aqueous. Well, let's check our phases. Aqueous is dissolved is going to be many, many more degrees of freedom than something that's a solid. Our last example, CO2 compared to HCl, these are both gases. Okay, let's try to look at one of our tiebreakers. Which molecule is bigger and more complex? Well, carbon dioxide has 3 atoms. It has a bigger molar mass. It's just a bigger molecule in general. It should have more entropy. Let's scroll back for just a second. We can also define standard molar entropy. This is a way to quantify exactly how much entropy a substance has at standard conditions. Those standard conditions, again, 1 atm for our pressures, 1 molar for our solutions, and usually 298 Kelvin for our temperature. We can utilize those standard molar entropies by taking a twist on Hess's law. Let's define the change in entropy for our reaction as the entropy of our products minus the entropy of our reactants. Well, entropy is a state function, so our plan for Hess's law still works for entropy, just like it does for enthalpy or other state functions. We can break our process down into some individual steps. The change in entropy for those steps will equal the change in entropy for our overall process. What that means is if we are trying to figure out the change in entropy for our reaction, well, maybe we don't know the exact entropy of our products and the exact entropy of our reactants at whatever conditions we're at, but the standard molar entropy is a known value for many chemicals. We can use this Hess's law plan, take the standard molar entropy for our products, and subtract the standard molar entropy for our reactants. This is a nice variation on Hess's law. Notably, our standard molar entropy, we can look this up for various chemicals. For pure elements, it's not going to be 0. The entropy is only 0 when we have a perfect crystal at absolute 0, which is not the case under standard conditions. We can visualize this if you have a solid and you melt it. Well, this process of melting is increasing our entropy. The change in entropy for this melting process has to be positive. Going the other way, if you are freezing, solid has less entropy than liquid. The change in entropy has to be negative. Final minus initial. Likewise, for evaporating, evaporating increases the entropy. Delta S is going to be positive. Or if you're going reverse, this process of condensing will have a delta S that is negative, a change in entropy that is negative. Yet another way of visualizing this, we can graph the amount of entropy in our substances. As you increase the temperature, the entropy changes a little bit, right? More energy from our temperature allows us to have more ways of arranging that energy, allows us to have, well, more entropy. Our phase change doesn't change the temperature, but it does drastically increase the amount of entropy present. So melting increases that entropy. As you warm up this liquid, the entropy increases gradually until we undergo another phase change where the entropy increases drastically. And so on and so forth. And again, we can rationalize this. Entropy is the ways that we can arrange our atoms, the ways that we can arrange the energy in those atoms. When we have a gas, there's lots of degrees of freedom. They're able to move and spin and vibrate. When we have a liquid, there's a little bit less motion, right? They're stuck up against each other, so there's less motion side to side. When we have a solid, we can only have vibration. As our phases become less condensed, there's way more places for us to put that energy, and therefore a lot more entropy. Let's look at some problems. Is the change in entropy positive or negative? To answer these, we can try to decide whether our reactants have more entropy or our products have more entropy. For the first problem, we have a solid on the reactant side. On the product side, we have a solid and a gas. The fact that we form a gas means that our products will have a lot more entropy. Remember, our phase is going to be our first thing to look at, deciding which substance has more entropy. This change in entropy has to be positive. For our second problem, we have 4 moles of gas that we start with, and we have 2 moles of gas that we end with. Going from 4 moles of gas to 2 moles of gas is going to decrease the amount of entropy that we have. Therefore, delta S has to be negative. For question C, we have a solid subliming into a gas. The fact that we have a gas means that we have more entropy on the product side. Delta S has to be positive. Lastly, we have 2 gases combining to form a solid, which means that delta S has to be negative. We can have a numerical example here. If we want to calculate exactly the change in entropy for a reaction, we can look up some values for standard molar entropy. Here's our reaction. Nitromethane burns in air to produce heat. We can calculate the change in entropy using our Hess's law formula. This is our formula. We get to use our coefficients in our reaction. We're going to add the standard molar entropy for our products and subtract for our reactants. These values are values that we can just look up, and they're given here for us on the slide. We can get our value. The change in entropy for this reaction is 177.9 joules per Kelvin. This ends up being a positive value, which we probably expect, right? We're producing more gas than we started with, and so our entropy should be increasing. And in fact, it is by exactly 177.9 joules per Kelvin. All right, let's leave it here for this video. We now have a way to define entropy and a metric for hopefully trying to decide if our reactions are spontaneous. We'll get into that in more detail in the next video. But please let me know if you have any questions, and I look forward to seeing you all then. Thanks.